There we go. Thank you, everyone. Our presentation today is predicting total tree height using a mixed effects random forest algorithm for diverse tree species in the Caribbean. My name is Tom Brandeis. I'm a research forester with the USDA Forest Service, Southern Research Station, Forest Inventory and Analysis Program based in Knoxville, Tennessee. And my colleague is Professor Sheng-Yi Yang from the University of Tennessee, the School of Natural Resources. Unfortunately, my colleague can't be here to present today. I'll do my best with his portion, which is the modeling itself, but my ability to answer some of the questions will be limited. So apologies for that. So a broader picture of the work that I'm going to be presenting here today, it's as part of a larger project of modeling growth and allometric relationships of Caribbean tree species using long-term permanent plot data. So I'll give a brief overview of these Caribbean island forests and why there is a need for this type of modeling work. Then I'll move into the portion from Dr. Yang and his modeling efforts. So these are the Caribbean islands from which we have data: Jamaica, the Commonwealth of Puerto Rico, Trinidad and Tobago, and the territory of the U.S. Virgin Islands. These islands have subtropical to tropical climates, depending on your classification system. One unusual feature is that they possess often very steep topographical environmental gradients. So the landscape and the forest types can change over very short horizontal distances, going from dry forest to evergreen, montane forest in short distances. Generally, these are broadleaf, both decidual and evergreen species with very few conifers, with some exceptions. They also feature very high tree species diversity with both native and endemic species and naturalized introduced species. In our inventory for Puerto Rico, we typically encounter over 300 species at a time with the possibility of over 700. Now, the land use history and forest management is also very interesting on these islands. Basically, they feature widespread deforestation across the islands with European colonization, followed by a period of agricultural abandonment and a shift toward other economic sectors, with the resulting natural regeneration of forest over much of these islands to varying degrees. There's very little in terms of plantations for wood production. However, these forests are extremely important for other ecosystem services they deliver, such as watershed protection. And why do we need these models? Well, we really have a need for developing allometric and growth models for these Caribbean species because accurate estimates of tree volume, biomass, and carbon are needed for land management and resource management, assessing hurricane damage and monitoring recovery, for our international reporting requirements for programs such as FAO's Global Forest Resource Assessment, and also for the UNFCCC's programs such as REDD+. And sometimes it's necessary to use these equations to reconstruct broken tops in trees or project growth. There has been some limited work done in the past, but our programs have primarily focused on temperate and boreal forests, of course. So we really want to try to leverage this permanent plot data to create some Caribbean-specific models. We brought together a team toward this end, initially led by Tamara Hartsey-Scalio of the U.S. Forest Service, with representatives from the different island groups. And we were all responsible for assembling our data and metadata from these permanent plots. I will skip over the Jamaica study sites because we don't use that data in this current effort. In Puerto Rico, oh, I'm sorry, I jumped ahead one too many. In Puerto Rico and the U.S. Virgin Islands, we're drawing data from an island-wide systematic sampling grid of permanent plots. We have 4 remeasurements in Puerto Rico and 3 in the U.S. Virgin Islands. All trees down to 12.7, I'm sorry, really down to 2.5 centimeters were measured on these plots and subplots. And we flagged trees that were damaged by hurricanes, an important point for later. The data from Trinidad comes from permanent plots established by their Forest Resource Inventory and Management section of their forestry division. These are larger plots, 1 hectare each, 144 of those. And some of these plots have trees on them remeasured up to 9 times at 3-year intervals. Now, I mentioned the project phases. Very quickly, phase 1, we're looking at predicting total tree heights from diameter measurements. Phase 2, we'll be looking at individual tree growth rates. And that could be for a presentation someday in the future to this group or in a publication. So as I mentioned, today we're looking at modeling height to diameter relationships. And here I'll have in a moment a quick summary of the statistics for the islands. I've highlighted a couple of points I wanted you to notice. 645 plots from which we collected over 37,000 measurements. The figure of the number of species, please keep in mind that it's really not 464 because there is overlap between the islands. Not that much, but we are in the range of about 500 unique species. You can also see here the range of data we had to work with. Note the total height in Trinidad is much higher. Rather, the mean total height is much higher in Trinidad than in Puerto Rico and the Virgin Islands. Now, in addition to this plot measurement data, we also have ancillary variables. We calculated some scan characteristics, including the quadratic mean diameter, number of trees, basal area, etc., and also a competition index, which was the ratio of the subject tree's DBH to a sampling unit level quadratic mean diameter. We also had 23 climate, topography, and superficial geology potential covariates that we were able to include in our models. Now, the main challenge we were really facing here was how to deal with the small sample size for uncommon species. And the first option we saw after reviewing the literature was data grouping. So aggregating the data on similar tree characteristics or taxonomies, functional or ecological traits. Option 2 was the use of mixed effects models. So using species and genus as a random effect in the model. And we chose to pursue that second option. So the main challenge in using parametric methods to build these models is the complex relationships among the many variables being tested. In our case, more than 20, which makes it difficult to determine appropriate model form and initial values for the model parameters. A possible solution to the problem of variable selection is machine learning techniques, like the use of random forest algorithm, so that we don't have to specifically identify the relationships between the variables in the model. However, the random forest algorithm has limitations. For diverse species assemblages, it can lead to high cardinality in the models and the potential for overfitting, as well as increased computation time. So we continue to explore other solutions. And we found as a possible solution in mixed effect random forest modeling, MRF, which includes the random forest algorithm in a mixed effects model. Basically, we replace the parametric part of the model with the random forest algorithm, which will give us the significant variables in the relationship while also incorporating species-specific random effects. So now I'll provide a very quick example of how the modeling process proceeded. First, we build a random forest with the transformed response. We subtract the random forest effect from the response variables. Then we use the fixed effects portion to fit the model with random forests. Next, we use the variables calculated from the fitted and observed responses to estimate the random effects. Finally, the estimates are updated to construct new transform responses, as in step 1, and then steps 1 and 3 are repeated until the parameters converge. In addition to the MRF approach just described, we also fit random forest models using parametric mixed model methods without including species that could serve as a baseline comparison. So for the sake of time, I won't go into these details, but this explains the packages and some of the details used behind all of the modeling effects. And now just to look through this flow chart of the model building procedure, we initially began with all our tree data and ancillary variables. These were included in both parametric random forest and mixed effect random forest models. This gave us variables ranked by importance scores, which were then sequentially added to submodels until we arrived at the final models. We then used that subset of variables to build parametric models with and without the environmental variables, something we needed for some practical applications in the future. And we found that two model forms, one for Puerto Rico and the US Virgin Islands, and another for Trinidad, work best for building parametric mixed models. And now we'll move on to some results. So here are the first of the variables selected, the key predictors in the final model. We see that DBH and competition index, CI, had the highest importance scores. In addition to the tree variables, we found that precipitation made an important contribution to all the models. Now let's look at the model's mean bias and root mean square errors. In general, all the models show unbiased selection. All the models show unbiased predictions, regardless of being parametric or non-parametric. But here we see that the root mean squared errors in Trinidad compared to the other islands and that of the MRF model produce slightly higher precision levels compared to the other candidate models. I'm sorry. I'm suffering from considerable lag in my computer, but now it's caught up. So now let's look at the mean bias and root mean square error by tree diameter class. We grouped DBH into three classes, small, medium, and large. The parametric model showed slightly biased predictions across all tree sizes and islands. We also found there was a lower root mean square error in the US Virgin Islands compared to the other islands. Here are graphs of predicted versus observed height for the different islands. Very tall tree heights were underpredicted, while very short tree heights were overpredicted in Puerto Rico and Trinidad. This was probably due to the large variation in total tree height at both ends of the data, which may result in biased prediction. Moving to the US Virgin Islands, generally the predicted heights were closer to the observed heights than in the other islands. But for Trinidad, we can see that the parametric models in particular had poor predictive ability, perhaps due to the smaller sample size and the possible inclusion of damaged trees in the data set, as I mentioned previously. There is a lot of variation in the measurements in the data, particularly for larger trees in the Trinidad data set. And as mentioned previously, they didn't collect damages while the measurements in Puerto Rico and the Virgin Islands did include indicators of damages, which has allowed us to filter out those unusual trees from the data set. And this could be the cause for some of this higher variation. So in summation, overall, total tree height was predicted without bias by random forest, mixed effect random forest and mixed effect random forest and parametric mixed models for all islands, but the MRF models improve prediction precision. Diameter and our competition index were the key predictors of the relationship to tree height. Precipitation variables were also important in predicting total tree height for these subtropical forests. And as I mentioned, We're looking forward to making practical application of these models to estimate original height of top broken trees that'll enhance our ability to quantify the loss of tree volume and carbon from wind damage and provide a better estimate of tree health and stand conditions after disturbances such as hurricanes. And then I have a couple of reminders from my colleague Sheng-Yi that mixed effect random forest is one of the many solutions for modeling height to diameter relationships. We aren't proposing an optimal model for species yet. For future study, we are considering investigating the model's sensitivity under different scenarios, compare the model performance among different species, and trying to include different ancillary variables in the model building. And for more information, particularly in regard to the model building, I would recommend you refer to our publication in Forest Ecology and Management, which will provide a much better explanation than I'm capable of today. And very briefly, our next steps now are to continue refining this modeling procedure and also move on to modeling growth on these species and including the Jamaica data and hopefully some data we just acquired from the National Forest Inventory Program across several Pacific Island nations. And with that, I will conclude and thank everyone for your attention.
Yeah, thank you, Thomas.